Let's talk a little bit about sequences and recall that our definition of a sequence is a function from a subset of the integers to a different set, usually something like real numbers or integers as well. And what we care about is the idea that normally it's going to be the natural numbers. I'm going to start at 0, and then I'm going to go to 1, 2, 3. And one thing that I can do is I can define it just a regular function as follows. I can have these three sequences, a sub n, saying, well, the nth term of my sequence is going to be 5 times n plus 3. Or b sub n, the nth term of my sequence is 2 to the n. Or c sub n, the nth term of my sequence is n factorial, where n factorial is n times n minus 1 times that all the way down to 2 times 1. So we can evaluate these sequences, and I can evaluate them in any order because I know a closed form like this. But for instance, I can evaluate a sub n. 5 times 0 plus 3 is 3. 5 times 1 plus 3 is 8. 5 times 2 plus 3 is 13. And I can finish evaluating the sequence as far as the values of n that I've specified. Again, I just plug in a value of n, like 3, and I can do 5 times 3 plus 3 to get 18. For b sub n, I can get 2 to the n, and I can again evaluate this step by step. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. And I can evaluate this sequence as well, using the function, the closed form, and evaluating it for each value. And then for c sub n, I'm actually going to do fewer terms of this one. C sub n factorial, well, there's actually a nice way of defining n factorial for 0. 0 factorial is 1. And the way I do that is because it's an empty product. And we can talk more about that later. But 1 factorial is also 1. 2 factorial is 2. 2 factorial is 6. So the factorial function grows very quickly. It starts a little small, but it grows very quickly. However, if I were to calculate 720, I had to multiply 6 times 5 times 4 times 3 times 2 times 1. However, if I also observe that 720 is really just 6 times 120, then that can help me out. Similarly, I know that 64 is 2 times 32, and 33 is 5 plus 28. These things are not coincidences. I can also define my sequences using recurrence relations, where this is the idea is I start with some base cases, some very initial values for my sequence, and then I can define my next term in terms of the previous ones. And this means that I can be very easy to compute elements of my sequence in order as long as I have all the previous values, but also that can be a lot easier than computing each one independently. So if I start with a0 being 3, I want to compute the next one. I will add 5 to get 8, add 5 to get 13, add 5 to get 18, add 5 to get 23, 28, and so on. For this b sequence, I can start with the number 1, and then I can take each number and multiply it by 2. So I take 1 times 2 is 2, 2 times 2 is 4, 2 times 4 is 8, 2 times 8 is 16, 2 times 16 is 32. And also I can start with 1 for my c sequence, and I can multiply it by my number n. So for c1, I'm going to take 1 times 1, I get 1. For c2, I'll take 1 times 2 to get 2. For c3, I'll take 3 times 2 to get 6. Then 4 times 6 to get 24, and then 5 times 24 to get 120. You see that these are actually the same numbers as I had in my previous definitions of these sequences using a closed form, but these recurrence relations do give us a very nice option for computing these numbers one by one.